Hey there folks, welcome back to another part of my thing where I'm making a Tetris Data Extractor. Well, I think we're finally to the end here. The end of this part of the series anyway. Last time we sent 124 tests through the algorithm, and I think we came across 3 or 4 issues with piece counts, the red numbers. And we were getting those misreads simply because my picture was too fuzzy. And when you're dealing with a capture card, like from a literal analog source, and then it's... Sorry, I'm looking at my screen. Why is it all wonky? Why did I lose my resolution? No. I'm not sure why that happened. Keep changes. Okay. Anyway, when you're going from analog video to digital video, analog video is not exactly the same all the time. And so it could just be an issue with my capture card. And that's fine. I'm willing to make that concession. We got the important numbers figured out. But the other thing that we saw last time were things were taking a little bit longer to run than I'd liked. And so I got rid of all the piece counts to just look at the score, the lines, and the level. And the long bar count, that actually was one piece count we kept. And that, you know, things were okay, between 500 and 600 milliseconds to analyze all that data. So there's still some slowdowns, and I mean, we also haven't tapped into the whole fact that this computer has multiple CPUs and we could harness that power. This is all a single threaded application right now. There's no async awaits, there's no nothing. It's just old school, a single threaded application that runs one instruction at a time, which we can change, and we might have to, which would be pretty cool. But I mean, it'd be pretty cool to implement. But let's actually take a step back. Well, is it taking a step back? No, we're pushing forward. We're going to take all the screenshots and make them available to the actual program itself, not just a test. And then we are going to run a profiler to see where the slowdowns are happening. So the first thing I got to do is I got to get access to all of my digits. And I think the best way to do that, although I wouldn't recommend it, is to, let me think. The Tetris Data Extractor tests do not depend on the Tetris tools. So can I add project reference to the tests? Is that going to work? That'll work. And then what? Actually, let's just build everything. Problem is, these screenshots are in the test project, and the test project yeah, you know what, this is gonna cause issues. Okay, screw that. Move. Okay, so I need the screenshots from the test cases. Let's just carry that over here. We'll paste them all here. I could actually put them into some shared part of the program so that the test can share it and the actual program could share it, but I don't want the actual program to share or to have access to these test cases all the time. This is just for our profiler's sake. So let's just make sure they're being copied. They certainly are. Okay, and let's see if we can't open one of these things up. So if we go test cases slash 100. Okay, and let's just write the data model. So this is the program. This is the actual program that we're looking at here. It's going to start up. It's doing a lot of things with the tests we're doing. It's beginning a lifetime scope. It's resolving the factory, creating the data model, and then just writing the data model. And the data model itself has, come on, a toString method, which I created that just spits out all the information. So that's what that is. So let's see if this works. We should see the console window pop up. There we go. Oh, right. I'm like, what? Can I increase that size? No. It's all wonky numbers, but that's because we have our app settings test, which we've changed again and again and again. And our app settings here. Yeah, they're different. Nope. Oh, for crying out loud, that's the tests. No, don't say that. The app settings themselves. There we go. But the fact of the matter is we saw it actually run and it spit out numbers. So it can find the screenshot. That's the exciting one. So it was one T number and that's it. Okay. One T piece. Can I increase this? Edit, properties, increase this font size. Better, I guess. Okay, so yes, we can access those screenshots. So what we're going to do is we are going to, I need all the okay, let's, yeah. See, sometimes I skip numbers here, so I can't just go, give me all the numbers, the things from 100 to 400. What I'm going to do is I'm going to, let's open up Google for a second. C# get all files in directory. I'm sure there's some simple directory.get files. Okay, search option. So there's a directory.get files method. Let's use that. Directory.get files. Second here, I spilled coffee all over everywhere and I'm still finding it in places. Okay, search pattern, what's that? Enumeration options, search option. No. The path is test cases. What's the search pattern? Oh, wildcard. Perfect. I want all the PNG files. Let's put a breakpoint here just to make sure we're getting what we want. Files is a string, arrays, and we have all these things. Test cases 100. I'm not sure why it says 126. Yeah, oh, okay, so it wasn't 124 cases, it was 126 cases. Excellent. That's all I want. Okay, what we're also going to do, this gives an array. So we're going to load up all of the things as bitmaps. So, because loading things up from the drive takes a long time, and I don't want that part of my profiling. So let's do this. Directory dot select. Yes, I want to use link. New bitmap. Bitmap X. Done. So this is going to go through each one of them, and let's call this bitmaps. Okay. And then we're going to begin a lifetime scope. We're going to have the data model factory. And then for each var bitmap, we're going to go through all the bitmaps and we're going to create a data model from the bitmap. Bitmap, okay. And then we are going to console.writeLine the data model. And because the toString method looks at each property, this will actually be an easy way. Because all the properties are lazy loaded, this is an easy way of visiting each one of those properties to make sure the algorithm runs in its entirety. That's it. That's all I need to do. And we're going to see a bunch of stuff spit out if indeed these bitmaps get loaded properly. So let's have a look at that. I'm assuming this will take a long time. That didn't take long at all. Why didn't that take long? Because it's enumerable, right? Because it's an IEnumerable, it hasn't been loaded yet. And I think that's okay. I could say toList to actually resolve the entire list and get it into memory. I'm curious how long it takes to load up 126 bitmaps. Not that long, actually. So there we go. We have each of them in this array. That's pretty fantastic. Okay. Now, let's run it. Let's see what happens to our algorithm when it's constantly running. We can actually see the game being played. Okay, fantastic. Let's kill that. Okay, now we are going to profile it. So, analyze, no, test. Where's my profiler? Performance profiler. I'll switch to release. Okay, so there's a lot more things in here in these new Visual Studios. all I really care about is CPU usage. Although this is cool, .NET Async, tool to investigate async await usage in .NET applications. I will probably be using some of that stuff to get some parallel execution happening later. Okay, that's cool. Tetris Tools is the startup project. So now we're just going to hit start. Actually, let's go back here. No, go back to our program. No, that's fine. I was going to say it takes time to output to the screen. I don't really want my... Yeah, let's just... equals data model. Data string equals data model. That's all I care about. We're not going to actually see it go to the screen because that's going to take time, and I don't care about the time it takes to get to the, to write on the screen. I don't want that muddying up my stuff. So okay, let's run this. Let's do it now. Where's my report here? Let's start. And this is going to take some time. What? That did not take any time at all. That's wrong. Something happened. Something's wrong. Yeah, no kidding. Okay, what I'm assuming is that because we didn't actually do anything with this, maybe the compiler said, well, I don't actually really need to do that. So, okay, let's go ahead and write it to the screen. There we go. There we're collecting data. So what's happening now is the algorithm is running, and every time it enters into a method, it saves, or rather, yeah, it makes a note, and then when it exits the method, it stores the number of CPU cycles that execution spent inside that method. And then when we're all said and done, we'll be able to look at where the CPU was spending most of its time. And we will be able to determine which areas of our code are using up the most CPU time, and maybe we can make them more efficient. So I suspect oh, it's getting faster almost, is it? I don't know. We're doing a, oh. What happened there? Okay, well, something happened. I'm not sure what. But we got enough data. So here we go. This is fantastic stuff. So graphics, 0.2%. The just-in-time compiler is 0.5%. The UI was 1.2%. The kernel is 18%. Now, kernel is your operating system stuff that you have no control over. But that's what we're interested in. So can I double click that, or how do we look at this stuff? Open details. Functions. Multiple modules. Reportedly, I don't know exactly how to use this. I mean, I kind of do. External code is 96%. Unwalkable functions. Why is that so expensive? Okay, so it spent most of the time of my code in here in digit recognition. That's the get probability function. Well, that's no surprise. What, maybe a call tree. This is not helping me out very well. Module. Okay, what I'm going to do, I'm a little bit confused. We're going to go back to debug. Because when we debug, when we run a program under the debug operator, don't save that. Let's just close everything. It shouldn't, it should keep all of its instructions, even if it determines that it doesn't have to. Because when I went like data model .to string. Okay, now let's run the profiler. And this time it's under the debug settings. But this is exactly what I want. I don't want it to be tossed away. And in fact, it's not getting tossed away. Okay, perfect. So this will eliminate printing on the screen. And I'm not sure how long to let this run. We'll let it run for 1 minute. I did not see what I thought I'd see. I don't understand the unreachable, unwalkable code pieces. So maybe this is going to give us less information than I wanted it to. One second, folks. We'll let this keep running. Ah, it's my face. Okay, we'll stop this and then we'll take a look. Load all symbols. Well, that didn't get me anything I wanted. That was almost pointless. I was excited to see a bunch of stuff. Unwalkable. 10% is unwalkable. 78% is in this external thing. Huh. What other... Well, I am disappointed, to say the least. This didn't show me anything I wanted. One second. I'm going to just do a quick search here. Profiler. Yeah, external code. Yeah, someone's got the same problem as me. What? When you have the diagnostic view up, look for a drop down. This is filter view. It's in the area below the graph, but above the list view. Click the drop down and check the show external code. Show external code. Filter. Show external code. Apply. Ooh. That's interesting. So the algorithm spends the most amount of its time in this thing? In the file system. And that's okay, because that's with me loading up all of the... loading everything up before the program runs. What's this? It's the file system as well. Okay, I obviously don't know what I'm doing. I mean, hide native code. Don't show external code. Apply. Right click. Load module symbols. Load all symbols. The digit reader, get probability. That's 3% of the whole CPU cycles. What's this? This is... What is going on? Okay, well, that was going to be a super exciting thing, but it's not anymore. Okay, what we're going to do, though, is I do have one more thing I want to try and fix. That was disappointing. I guess I need some lessons on how to use that profiler. All right. One more thing that we're going to try and do to speed this up is the digit reader. So what we do here is when we get the probability of a digit, we go from 0 to 9 and we get the probability, and each one is done in lockstep. So first 0. And then 0 has to finish until we compare it to 1. And then 1 has to finish until we compare it to 2. And this is, you know, like it would run on a single CPU. But we have many CPUs, and we can let the computer decide which one to run it on. And in fact, there's no reason why we can't just do these all at once. Just say, hey, these 10 things, just start running. And then we're going to all reconvene when we're all finished. So that's what I want to change. This method to use some parallel, using the task parallel library, we can get this stuff happening at the same time instead of waiting for one to finish and another. So this is how we do that, and I'm not entirely sure how easy this is going to be, but there is a library the task library, and no, it's the task parallel. I have to remember. Is it parallel? Parallel. Yeah, 4 from inclusive 0 to exclusive. The end index, which is exclusive, so that would be 10. The action is get probability for reduced image oh, this is, wait a second. This is an action, so this is an index. This is get probability for reduced image index, character width and character height. So this parallel 4 okay, so that's that. So it's going to go from 0 to 10. This is the thing it's going to do. Okay, the first thing I need to, when you start using the parallel library, you have to make sure that the data structures you're using can handle things happening all at once to it. So I'm not sure if a list is thread safe or not. thread safe collections. Concurrent. Let's have a look at this guy. This is from 8 years ago. 9 years ago. Yeah, let's use a concurrent bag instead of a list. Okay. So a concurrent bag lets you not worry about different threads accessing it all at once. So that'll be fine. So probabilities we're going to add, and that's okay. This is going to be, we can actually make it a list at the end. Let's comment this out. Now, how do you actually execute this? I don't even know. Executes a for loop in which iterations may run in parallel. And then it brings back this parallel loop result. Lowest break iteration. Okay, let's go back to the Googles. Parallel.for. Yeah, that's exciting. Okay, examples. Parallel.for. We do all this. Var result. It does all that. Lowest break iteration. Break and iteration. What's the for each? Oh, no, that's fine. So we're actually okay. The parallel loop result. Okay. So but do I have to await it? Or does it just do it automatically? Okay, well, let's done. Let's just see if this works. So let's put a breakpoint here. And then here we're going to put a breakpoint. We'll run this. Okay, so here we are, our probabilities of nothing. Then we're going to step over this. Object is currently in use elsewhere. course it's currently in use because we're using it. That makes sense. We can't I guess we can't use the same because we're using the same reduced image here for each one of these. That's okay. That is absolutely okay. Let's okay, before I do anything else, I need to see what I've done, what I've changed. I've actually changed too much. No, I've got to go into let's see here. I've modified lots of those. I've added the test cases. I've actually added the canonical digits. Oh my goodness. So I didn't even commit what I did last time. That's a scary thing. Okay. Let's put this back to what it was. I didn't realize I didn't do this here. The tests, let's undo this. The app settings is good. The program, yeah, we'll keep those changes. The canonical digits. That's fine, and that's fine. Okay. Let's see what we've got now. I don't really want to add the test cases though. That's not a thing I want to be added. Okay, so let's stage that and that. We'll stage all of these. But I don't want... Where's my... Oh, I want to stage this, but my program and the project and all these test cases, I don't. Okay. Good, that looks good. Canonical image class. That's what I did last time. Okay. Time we got here, 44 minutes. Okay, so let's actually... So instead, okay, we got two things, because we can also say, well, I also need to look at the score. When I look at the score, I look at each digit, right? But I don't have to, I don't have to figure out the first digit before I figure out the second digit. So these can be parallelized as well, I hope. Hopefully we don't have shared resources with this. So let's actually parallelize the digits being investigated. Where am I here? Digit reader? No, get digit. Here. So the digit image is a clone of that. All right. What we're going to do is we're going to chop up the screenshot. So here we get the sub image of the screenshot. This is the bounding box where the number is contained. All right. The final number is an empty string. The character width and the character height are there. I'm going to chop up the the sub image into its components now. So the digit crop, the digit image. Why do I? Oh yeah, this. Okay. And then digit. So this takes a while. So what we're going to do is, we're not going to actually run this in the loop. What we're going to do is the loop is going to create a dictionary. So we're going to have our dictionary. Actually, no. A bag equals new concurrent bag of tuples, and the tuple is going to be an integer index. This will be what number, is this the first digit or the second digit or the third digit? And then this is going to be the bitmap of the image, and this is going to be the result. And I think what I can do, instead of doing this, I can do this. Index, bitmap, digit, image, and string result. Okay, so that's a bag. I can do this now and say bag dot add the column number followed by the digit image followed by an empty string. That's what we're adding. And then we're going to say parallel dot for each everything in the bag index digit image result Can I actually assign the result to be something else? I don't think so. I don't think I want to deconstruct this. Digit info, because now I can have access to the result and I can set it. Okay. So for each of these, we're going to say digit info dot result equals the digit reader dot get digit from the digit image and then the character width, oops, character height. Okay. And then once I've done that, we'll have some other funky things to do. So let's actually run this. This video went from being the most exciting video I could think of to being one of the most boring. But if I can parallelize some of this, it's gonna, I think it'll work. So I have this bag now, and it's got 6 things in it because this is a screen score, right? And let's see if this will run. Object is currently in use elsewhere. What are you talking about? Huh. Oh. Oh, I see. So the issue is because I am using the exact same canonical digits, only one thing can take a canonical digit and scale it to produce a new image. So what I need to do, because when I call my scale image function, I've got the original here, and this is one of the 10 canonical images. And apparently I can't do this while it's being used by something else. This actually... Does this create a new bitmap? This clones it. Okay, I have to check for one thing here. C# bitmap. I need to see here. Image size initializes a new instance of the bitmap class from the specified existing image scaled to the specified size. So that does create a brand new image. But the problem is I'm trying to use it multiple times. So what we can do here, we might have to lock usage on that particular resource. So the way we do that is we say, look, I'm going to get the canonical image, then I'm going to scale it. Here, I can actually... And then I want to reduce it. So right here, getting the canonical image and then scaling it is something that I need to do all by myself. Another thread can't do the same thing. So we need to lock it somehow. Private, so we can set up a lock object here. Equals new object, and that's just a pathetic nothingness here. It's literally an empty object, but we're going to use it to lock. Oh, not object. Lock. This. So what we're going to do is we're going to say bitmap scaled canonical image. Okay, this should work. So if you hit here and something else has locked the object, you have to wait your turn. Once you get your turn into this section, only you can execute. Everything else is waiting. So this will help us to wait while we grab the canonical digit and scale it for our own purposes. So now this should work. Thing is, once you have locking and waiting, you lose some of that speed, but I think the overall gain is going to be better. Let's go right here and see what we see. Whoa, see, that worked. Totally worked. And now the bag, do they have results? No, they don't. Okay, well, that's fine. Set doesn't exactly work. So we can get rid of that. We can say index digit image here. This. What's the problem? Cannot convert. Huh. Oh, I think I need to do double it up. Int index bitmap digit image. Is that right? Why can't I deconstruct this? Oh, come on. Fine. Digit info. Fine. And then I guess we're going to need to have a how do I want to store this? Digits in string. I don't know. And then digits of digit info index. Does that work? And now I have an index of digits, and so now we'll say final number equals digits dot select I mean, what I could do is this. I could, yeah, you know, this is probably, never mind. No, I want this. Oh gosh, it was a bit trickier than I thought. Okay, so I want to go through each of the key value pairs in the dictionary. Order by index. Actually, can I just do this? Order by kvp dot key dot select x. Let's be consistent here. kvp dot value. Sorry, I'm thinking very much here. So we order by the key, which is the index value. And the reason we have to do this is because we might send off the 5 digits or the 6 digits that are the score. We're going to get them back in just bizarre random orders. So we can't guarantee that the dictionary is ordered here. So we order by the key, and then we select the value, which would be a string. And then we join them up, and we parse the final number. I want to put a breakpoint there. Let's get rid of all my other breakpoints. Okay, let's try this. Whoops. So what are in my digits here? So this keeps on going. Am I getting any other values other than... Because everything is 0. I want to see some non-zero value. Let's just pick one of them. Let's pick 310. Well, here. Yeah. Let's get rid of all these. Yeah. Okay, so now we'll start at 310. I want to see some non-zero digits happening here. Perfect. So here we've got oh, interesting. Yeah, so I did it wrong. So the 0th digit is 0. The next digit is 8. The next digit is 2. So 8, 2, 3, 4, 4. 8, 2, 3, 4, 4. Is that what 10 is? 8, 2, 3, 4, 4. So that tells me that our... Yeah, this is wrong. I want to go digits dot values order by x. What's the value? Oh, wait a second. No, what am I talking about? That's totally right. That's absolutely right. Sorry, folks, I got a brain fart there. I forgot the way the debugger showed. 82344. Perfect. The next number is 15 because the digits came back as 1, 5. Okay, this tells me okay, so we've parallelized each of these specific digits. Okay, I'm curious about the tests now. To be fair, I'd really like to see these tests run a lot nicer. So let's have a look at that. I think last time we saw like a 1.04 seconds per test after we did the file I/O stuff. Now we're getting many sub-second tests with all the piece counts. Oh, but there's still 1.8s and 1.6s. There's a 2.4, so maybe it's not as fantastic as I thought. Oh, weird. Okay. Let's stop these tests. That's not working exactly as I wanted it to. Okay, we should put an end to this video. It's been a long, boring one. What did we end up doing though? We ended up parallelizing one section of it, and I don't even know if that did a whole lot. Okay, just to make myself feel better, let's not look at the unimportant data. Let's run these again. Last time we were seeing between 500 and 600 milliseconds. I'd like to see something a little bit smaller than 500 to 600 milliseconds. That would be nice. Okay, so that's nicer. I would say we're getting values of 300 to 500 milliseconds with a few larger ones thrown in there for good measure. So we did gain some ground by parallelizing that small bit. Here's the 6 digits of your score. Send them out and let them get recompiled back when you're all finished. I still am seeing 1.3s, 1.1s. Let's just run all these tests. What I'm curious about is why this says there's 124 tests in the group, but there were 126 files. Oh, no, I don't know. Okay, so we ran all those tests in 1.1 minutes. Let's open up my calculator here. 1.1 minutes divided by 124 equals times 60 seconds per minute. So we're getting these things in about 0.53 seconds. 530 seconds or milliseconds to figure out all these things. And that's okay. That's decent. And I think because the score is 6 digits long, that's probably, we're going to save the most amount of time on that one. It's too bad I couldn't get this to work. And the reason I couldn't get this to work is because we're using the same reduced image. For each one. Let me try something very quickly. Actually, let me go back here. Get the probability list. The reduced image. We're taking the reduced image. And why are we doing this? Because we're reducing the image here. I wonder what would happen if we didn't reduce the image. Because the problem is No, I think we do need to reduce the image. So we come in here and we get the probability for the reduced image. And doing so, the reduced image is used when we get this probability. But look at here, like, one image taller and wider, like these kinds of things are, all the work is being done in these methods, and if we have to lock the objects before we use it, like we're not going to get the benefit of parallelizing this stuff. The other thing we can do is we can just say, okay, I need 10 versions of my reduced image. I pass in my reduced image here. See, I reduce it. How much would it take to just make 10 copies of this image? Oh boy, it's been an hour and 20 minutes. We got to get this done here. All right, it's not as much as I thought I'd get done today, but it's okay. We're going to stop it here. My hope and my goal was that next time we'd start a new era in my project, leaving behind this algorithm and starting to use it in various applications. I think we will do that. This is an interesting issue because of the way we've written this. If we need to fix it more, we can come back later and fix it. But it's working, it's fine. Looks like we can get all the important pieces in about 500 milliseconds. So definitely we're under that 1 second mark. So I think we're going to stop there for now. And I'll think about it more, but I think next time we're going to push forward into the next phase of this project, which will be using the Tetris Data Extractor to analyze a live video feed of a game, ultimately to give score updates and Tetris rates and weird statistics you don't get from the game screen, and also to hopefully have a robotic announcer back you up when you're playing. I think that would be very, very enjoyable and humorous. So that's it for me. This was long and boring, so if you stuck through the whole thing, you're a hero. You're my hero. Have a nice day, and we'll see you next time.